Well, hello, chemistry students. Let's get started with today's lesson, the photoelectric effect. That is lesson 6 in your study guide. So if you'll get out your study guide, we'll get started here in just a second. All right, lesson 6, the photoelectric effect. Now, I want to remind you that in our previous lesson, we talked about Max Planck's quantum theory. And remember that Max Planck developed his quantum theory because classical physics could not accurately predict the electromagnetic radiation that was being emitted by black bodies or by objects in general. And so he essentially threw out some of the ideas of classical physics when it comes to light and had to develop some new ideas that became known as the quantum theory. And the quantum theory, even though Max Planck's like, man, I don't know. I don't know how this works. I don't even know why it works. But the fact is that if I apply quantum theory to emitted light from objects, it works, and it works well. All right. Now, at this time, the black body problem and emitted light from atoms was not the only issue that seemed to be coming up with classical physics. Another experiment that was being done was known as the photoelectric effect. And in this experiment, scientists, physicists, and chemists were using classical physics again to make predicted outcomes. What were the outcomes of the photoelectric effect based on classical physics? But as they performed the experiment, the photoelectric effect, the results, the observations did not jive with the predictions of classical physics. So here we got a problem, and another problem with classical physics, a serious problem, in fact, right? So I want to talk about what the photoelectric effect is, the predicted results based on classical physics, and the real actual results, and then the final conclusion of what's really going on with the photoelectric effect, okay? So here we go. So first of all, I want to, before we even really get much into the photoelectric effect, we need to understand a little bit more about light intensity. And we're just going to kind of keep it to the basics. So what I would do is in your study guide, write this idea of intensity down. The intensity of light depends essentially on the amount of light. So the more light you add, the higher the intensity becomes. So the more light emitted, the higher the intensity or brightness of the light. And so how bright light is and the intensity are kind of related. The more light we have, the brighter the light appears to us, the higher the intensity. So higher intensities results in the amplitude of the standing wave increasing, all right? And this should result in a higher amount of energy. So what we're saying is that if I add more light, the intensity of light goes up, which means the amplitude of the wave increases. And as the amplitude goes up, so should be the amount of energy that the wave has. And this is a classical physics idea. So in other words, at low intensities, the result would result in low energy waves, and at higher intensities would result in higher energy waves, okay? It's kind of how you can look at it. Also, the brighter the light means it, or should mean that you have more energy than a dimmer light, okay? These are all kind of classical ideas or thoughts, okay, in this. All right, so when we maybe think of this, a quick analogy of light intensity using water waves instead of light waves. So if you've ever been to the ocean and you've seen the waves in the ocean, you'll notice that small waves that have low amplitude, when they hit you, they don't seem to have a lot of energy. They don't move you as much. But as the wave amplitude gets higher, the higher the crest of the wave, when they hit you with more force and have more energy, and you seem to move like a tsunami. If you have a tsunami and it creates these huge waves that are just lots of energy in those waves, and when they hit, they're very destructive. Okay, and so um, classical physicists looked at light waves being in the same manner, that if I increase the intensity of light, adding more light, the amplitude should go up, so therefore the energy of the wave should also increase. Okay, classical idea. But is this correct? Let's find out. All right, so the photoelectric effect, the basic idea is very simple. Um, Essentially, we have a object, usually a metal object, and the metal object, of course, is made up of atoms, have electrons. And essentially what we want to do is build up the amount of electrons on the surface of the metal. So the metal plate becomes very negatively charged because of a lot of excess electrons on it. And then what we're going to do is we're going to shine some light onto that metal surface. And as a result, we want to eject those negative electrons from the metal surface by using light, essentially, to do so. And then what we're going to do is we're going to measure the velocity of the ejected electron. So how fast that electron is being ejected. Because if we know how fast the electron is being ejected, then we know how much energy that electron has. And so what we think is happening is that the energy that is in the light source that shines on the metal surface, that energy is going to be transferred to the electron. And so if we know the amount of energy that the electron has, then we can say we know how much energy that the source of light had originally before it transferred the energy to the electron, essentially. The other thing we're going to measure is the number of electrons that are emitted when the light hits that metal surface. So those are the two things you got to look at, is the speed at which the electrons are being ejected and the number of electrons being ejected in this photoelectric effect. All right, so this is more or less the actual experimental setup of the photoelectric effect. And it looks very much like a cathode ray tube in some respects. So you have a metal material that is referred to as the anode, much like we saw with the cathode ray tube. And we have another piece of metal that is the cathode. All right, and essentially the anode and the cathode are going to be connected to a battery. Okay, now by doing that, it's going to make the anode very negatively charged. Okay, so I'm going to put these negative charges, meaning that we have an excess of amount of electrons on the surface of that anode. The cathode is going to become very positively charged. Okay, so I'm going to put a bunch of positive charges here because it's connected to the battery. One of the things you can think of is the cathode can be called the collector and the anode can be called the emitter. And the reason why is because when light is shined shines on the anode, remember we want to eject those electrons. And so the electrons are going to be emitted from the anode or from the emitter. And then those electrons are going to move from the anode to the cathode, which is positively charged. Again, this looks very much like a cathode ray tube. Essentially, though, the problem is that we're going to get rid of all of not only the air inside, but there's going to be no gas inside. And so because of that, electrons should not automatically flow from the anode to the cathode. And so that's where the light comes into place, because if we can shine some light onto the anode, that the energy that the light has should transfer to those electrons, and then the electrons then are able to be ejected from the anode or the emitter to the cathode. Okay, now when those electrons are ejected from the emitter to the collector plate, what we're going to do is measure those two things. We're going to first look at the velocity of the electron being ejected by using what is called a voltmeter, okay? And the voltmeter is going to measure the velocity of the ejected electron, which then will tell us the energy that the electron has. And we're going to use an ammeter, and that's going to basically measure the number of electrons that are being ejected, okay? So these two things, these two devices that are connected to our experimental tube here, essentially, is going to measure, again, the velocity of the ejected electron, that's the voltmeter, and the ammeter is going to measure the number of ejected electrons, okay? All right, so hopefully you kind of get the experimental setup for the photoelectric effect here. All right, so what we're going to do is we're going to actually watch a video, and while you're watching this video on the photoelectric effect, you're going to fill this table out in your notes. And essentially here on the left-hand side, you're going to write down what was predicted by physicists would happen with the ejected electrons when light shined on them. Okay, so essentially, we're talking about the predictions using classical physics, and so you're going to write those down here in this left-hand column. In the right-hand column, where it says what really happened, that's where you're going to write down what really occurred. What were the real observations of the photoelectric effect and what really happened, okay? So you're just gonna write those down as you watch the video. If you need to pause the video so that you have time to write what should happen and then what really happened, that's fine, okay? So let's do that. Let's get to the video. All right, here we go.
How to describe the photoelectric effect? Proved the quantum nature of light, won Einstein a Nobel Prize, spawned a whole new field of physics, revolutionized the way we view the entire physical world. Yeah, it's a pretty big deal. Hey guys, Jade here. So, the photoelectric effect, the effect that proved that light was made of particles. So you're thinking, what do you mean light is made of particles? I mean, it doesn't look like a particle. But more importantly, in 1801, Thomas Young proved that light was a wave. We had light doing all sorts of wave-like behavior. Wave interference, wave diffraction, there was an interference pattern. All the evidence pointed to light being a wave and not a particle. It even proved super genius Isaac Newton wrong. So now let's take a look at the experiment that proved the quantum nature of light, or that light is a particle. Either way. So we've got a metal plate which we're going to call the emitter. You'll see why in a sec. The emitter plate is connected to the negative terminal of a battery, making the emitter plate negatively charged. Now we place another metal plate opposite the emitter, which we're going to call the collector. The collector is connected to the positive terminal of the battery, making it positively charged. Now, the electrons in the emitter want desperately to jump across to the collector. Opposite charges attract, so the negatively charged electrons want to get to the positively charged collector. But there's a catch. This setup is placed inside a vacuum. Nothing's going anywhere. The electrons are stuck to their metal plate, no one can move. Of course, if the electrons were to somehow break free of their metal prison, they would jump the gap no problem. But first, they need to be given enough energy. This is where our light source comes in. A light is shone onto the emitter plate, freeing the trapped electrons. The energy carried in the light is transferred to the electrons, giving them the energy they need to jump off the emitter toward the collector. We can measure how many electrons are jumping off the emitter and onto the collector by placing an ammeter in the circuit. The flow of electrons produces a current, which is recorded by the ammeter. The bigger the current, the more electrons jumping off. So before we reveal the experimental results, let's take a look at what classical physics, or Young's theory that light is a wave, predicts should happen. If light were a wave, the amount of electrons jumping off the emitter should depend on the intensity of the light. Light of higher intensity means a wave of bigger amplitude, which means a wave carrying more energy. So a higher intensity should produce a larger current. So if we turn up the intensity, regardless of the frequency of the light, the electron should be given enough energy to break free. Also, if light were a wave, this energy transfer should be somewhat gradual. So there should be a time delay between when the light hits the electron and when the electron is ejected, especially at low frequencies. Another thing that should happen is that as the wave amplitude increases, more energy is being carried in these waves, so the electron should have more kinetic energy as they jump off the emitter. This means that as the intensity of the light increases, the electron should travel with a higher speed toward the collector. Yeah, none of that happened. Sorry, Young. It was observed that as soon as the light hit the metal, the electrons jumped off the emitter instantaneously. There was no gradual buildup of energy. It was like the electrons were getting knocked off the surface. But the most mind-boggling observation was that the kinetic energy of the electrons was found to depend on the frequency of the light, not the intensity. In fact, for some frequencies, no electrons jumped off the metal at all. The only way to explain this behavior is that light is made of particles. It's like if an electron were this melon and different frequencies of light were this delicious assortment of organic produce. There is simply not enough energy in this cherry tomato to knock the melon off the table. You can turn up the intensity as much as you like, but no matter how many cherry tomatoes you throw, that melon is not going to budge. What about a clementine? Still no. Now let's try the lemon. Yes, looks like there was enough energy in this lemon to knock the melon off the edge. This is what's called the threshold frequency, the minimum frequency needed to knock the electrons off the surface. All frequencies above the threshold frequency carry enough energy to knock the electrons off the surface, but all frequencies below the threshold frequency, well, they just can't get the electrons to budge. The kinetic energy of the electrons was dependent on the frequency of the light, not the intensity. The higher the frequency, the more kinetic energy. It didn't matter if the light was barely aglow or so bright it's blinding. The kinetic energy changed only with the frequency. From this, Einstein concluded that the energy carried in one of these light particles, which he called photons, was also proportional to the frequency of the light. More energy in a single photon meant more energy being transferred to an electron. The one thing that did depend on the intensity was the electron current. If the light shone was above the threshold frequency, a higher intensity caused a larger current to flow. And this makes sense. I mean, a larger intensity means more photons. More photons means more photon-electron interactions, which means more emitted electrons. Einstein's discovery of photons won him the Nobel Prize and kind of revolutionized physics. Oh, okay, so you're saying light was a particle, Einstein was right, Young was wrong. Light is a wave. Pfft, what a stupid idea. Well, actually, it turns out they were both right. Light is a particle and a wave. Welcome to quantum physics. Light sometimes acts like a particle and sometimes acts like a wave. This phenomena is widely accepted among physicists, and it's even given its own fancy name, wave-particle duality. But it doesn't just stop at light. In the quantum world, particles and waves are doing this all the time. An electron can have a wavelength and frequency, and a wave can collapse into a point like a particle. Don't get it? Don't worry. As brilliant physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum physics." And he won the Nobel Prize in quantum physics. That's it, guys. Thanks for watching. I hope you
All right, so hopefully you took down, I'm going to go back to our PowerPoint here. All right, so I hope you got some good ideas about what should happen based on classical physics and light being a wave and what really actually did happen, okay? So let's actually, here's a list of some things that I came up with and see if it sort of matches what you came up with. If not, you might want to add a few of these ideas in there. All right, so first of all, what should happen if light is a wave based on classical physics? First of all, I put the amount of electrons should depend on the intensity or how bright the light is. Frequency should not be a factor. In other words, it basically predicted that frequency should not determine the number of electrons being ejected, but only the intensity of the light, okay? In other words, the more light there is, the more electrons that should be ejected, okay? And that's actually not too bad of an idea because it actually really does fit what really did happen there. But what about these other ones? At higher intensities, electrons should be ejected at higher and higher kinetic energies regardless of its frequency. Meaning, again, the frequency should have no impact on the energy that the ejected electron has. Instead, it should all be about the intensity. The more light you have, it should be able to transfer. So the more light you have, right, the more energy that light should have then. And therefore, more energy is being transferred to the electron. And so forth, it should be ejected at a higher velocity. That's what classical physics, again, is predicting, right? If the amplitude goes up, it should have more energy. If it has more energy, that energy is being transferred to the electron. Therefore, the electron should have more energy when it's being ejected and should be going at higher speeds, okay? So it makes sense, right? Based on classical ideas. So at higher intensities, electrons should be ejected at higher speeds then. There should be a time delay before the electron is ejected, and that is because when the wavelength, so pretend this is an electron, when the wavelengths or the waves are hitting that electron, it's transferring energy directly to the electron. And it's going to take some time for that electron to build up the right amount of energy for it finally to be ejected, if light is a wave, okay? Especially that would happen at lower frequencies, okay? So those are some ideas that I wrote down based on the video of what should happen if light is a wave. But what really did happen, okay? What were the actual experimental observations? Number one, there was no time delay whatsoever. It's as if the light hit the electron and immediately transferred all of the energy to the electron and immediately ejected it, okay? Which is a big point against classical physics and that prediction right there. Another one is that kinetic energy actually depended upon the frequency and not the intensity. So in other words, what was shown then is that you can add all the light you want, and it did not affect the energy that the electron had. It only was when you changed the frequency that it actually changed the amount of energy the electron was happening. So for instance, if red light was shine on an electron versus blue light, well, it was shown that blue light has a higher frequency. You know that. Blue light has higher frequency than red light. And so therefore it seemed that the higher the frequency, the more energy that light actually had and was transmitting to the electron. And indeed that is actually really true, okay? So at lower frequencies, you have lower amount of energy that the light has, okay? And as the frequency begins to increase, so does the energy that light carries. So we would assume then, based on that idea, that that red light would transfer a smaller amount of energy to an electron than blue light. And blue light would transfer a smaller amount of energy to an electron than, say, violet light or ultraviolet light even, okay? So therefore, it seems that certain that frequency, a certain frequency electron will not be ejected no matter how high the intensity was, okay? So what do we mean? Well, at lower frequencies, because it's that energy of light is based now, we understand that light energy is based on its frequency. At some frequencies, because they just don't have enough energy, they do not have the ability to eject an electron. No matter how much light we can add so much light that it's so bright, but it won't matter. It won't eject an electron because it's not transferring enough energy. And that is because the frequency is not high enough to have enough energy to transfer to the electron to eject it, okay? So I hope that makes sense to you. We'll look at that a little bit more in a minute. The only thing that did increase with increasing intensity was the number of electrons being ejected. And that's an important point that we'll look at a little bit later here. All right, so here are some important thoughts then that we need to look at, okay? Should write these down. So we have three scenarios that are essentially this diagram is showing, okay? So we're gonna say scenario 1, scenario 2, or in other words, experiments. Maybe that would be a better term. So we have experiment 1, experiment 2, and experiment 3. And we're simplifying this photoelectric effect by just using flashlights. And so we're essentially shining light from the flashlight onto the surface of a metal object. and we're going to look at not only the number of electrons being emitted, but the amount of energy those electrons are being emitted, okay, based on its velocity. So if you look closely between experiment 1, experiment 2, and experiment 3, and you look at the wavelengths of light being emitted, what do you notice is happening from 1 to 3? If you say that the wavelength is increasing, you would be correct, okay? So in experiment 1, we're using low or small wavelengths of light compared to experiment 2, and then experiment 3 has the larger wavelengths, all right? So if that's the case, which experiment has the highest frequency wavelengths? Well, that would be experiment 1, right? So what we're gonna say here is the frequency, F for frequency, the frequency is increasing as we're going from experiment 3 to experiment 1, okay? So that's important as we look at these results here. So experiment 1, when we looked at the amount of energy coming off of these electrons, so when the light of experiment 1 at these high frequencies, the electrons being emitted had a much higher energy than the electrons in experiment 2, all right? And then in experiment 3, there was no electrons being injected, okay, at all right? So the frequency here was not high, did not have a high enough energy, related to a high enough energy to cause any ejected electrons, okay? So when we add more light, that looks like adding more flashlights, okay? So when I'm adding more light, remember, by adding more light, I'm just increasing the intensity, okay, or the brightness. And so 2 flashlights would add more light than 1 flashlight, okay? So what would happen if I increase the intensity, right? By adding more flashlights. Do we see much of a change? Well, what we see is that by adding in experiment 1 to the high frequency light, by adding a second flashlight, it did not, and this is super important, it did not change the velocity of these ejected electrons, okay? So regardless if you had 1 flashlight or 2 flashlights, the energy of these electrons was the same, okay? So these electrons here had the same energy as these electrons here, even though there's more light. So we begin to see that intensity seems not to really change the amount of energy that light has, not the intensity. We see the same result in experiment 2. In experiment 2, when we add 2 flashlights and we compare the velocity or the energy that these electrons have with 2 flashlights versus the 1 flashlight, we find that they have exactly the same energies. They're being ejected at the same speed, regardless if I have 2 flashlights or 1 flashlight. In fact is, even if I had 3 or 4 or 5 flashlights, it will not change the energy that those electrons have. So it appears that there is something more to do with the frequency than with the intensity, okay, which is very, very contrary to classical physics. Now, comparing number 2 and number 1 experiment, no matter what, in number 1, the electrons, regardless of how much light, the electrons in experiment 1 are always going to have more energy than in experiment 2. And that is because the frequency in experiment 1 is higher than in experiment 2, okay? So as the frequency increases, so does the energy that the light has, okay? And I'm just gonna write this down here, okay? So it seems like as we increase in the frequency, we increase the amount of energy the light has. It has nothing to do with amplitude, nothing to do with light intensity. No matter how much light I add at a particular frequency, it will not change the amount of energy it has. It's all based solely on the frequency. Now, this is really very different than classical physics predicts, okay? In experiment 3, no matter how many flashlights we add, we can never get electrons to be ejected at these wavelengths or these frequencies, which tells us that the frequency is too low. Therefore, it has a too low of energy to cause the electrons to be ejected at all. So I could add even more flashlights to experiment 3, and I still would never get a single electron ejected ever in experiment 3, because it does not matter about the intensity of light, it only matters about the frequency of light. And since experiment 3 has a low frequency, therefore it just does not have enough energy in order to eject an electron ever, okay? Now, what this experiment does show us, the only thing it shows us as far as intensity is concerned, that if I increase the intensity, the only thing I get more of is the ejected electrons. So I get more electrons being ejected with 2 flashlights than with 1 flashlight. And I see that with also in experiment 2. With 2 flashlights, I get more ejected electrons than with than with 1 flashlight, okay? In experiment 3, it doesn't matter. Again, I can add as many flashlights as I want. I'll still never get an ejected electron because at that frequency of light, it just doesn't have enough energy to eject an electron, okay? So all of these results that we're seeing and talking about here were not really predicted by classical physics, and therefore could not be explained by classical physics. Everyone was scratching their heads. What the heck is going on here? These results from the photoelectric effect just are bizarre. They don't even jive with classical physics at all right? So not only do we have a black body radiation problem with emitted light from atoms, but we also have this strange outcome of the photoelectric effect. What's going on here? Well, by the time the photoelectric effect has been studied intensively, Max Planck has now published his quantum theory. Scientists as a whole don't take quantum theory very, they're not very excited about it. They don't think much of it, including again Max Planck. So along comes Albert Einstein. All right. Now Albert Einstein, as a young student, he is very fascinated with light, extremely fascinated. He loves the violin, and he loves light, and he loves to study the nature of light. And so he begins to see there are problems with classical physics in the predicted outcomes of some of these experiments. And he begins to wonder why, what's going on. Now, Albert Einstein was a genius, absolute genius. Always the smartest one in the room. And he was actually even smarter than his professors. And when Albert Einstein began to question classical physics a little bit and questioned some of these outcomes, and asked his professors, well, let's look at this. His professors really didn't want to deal with it. They didn't want to deal with these problems with classical physics. They really didn't. They wanted to sweep all of this under the rug, or really pretend that in some future day, classical physics would eventually have an explanation for the outcome of the black body's radiation issue, and specifically the photoelectric effect, and other experiments that we haven't talked about. But Albert Einstein was persistent. He eventually, at time, he kind of gave up with his professors. In fact, his professors, the professors of Albert Einstein and Einstein himself, they eventually started not getting along. And Einstein just kind of refused to even care about what they were saying anymore. Albert Einstein will graduate from college, but because of his bad relationships with his professors, he really does not get any strong recommendations from them. And so therefore, he really doesn't get a prestige job, and at that time would be a professor at some university teaching physics and doing what he would want to do, and that is theoretical physics, and trying to understand more about not only the nature of light, but really how the universe works in general. And that's really what Albert Einstein wanted to do. He wanted to know how the universe worked. And that was the key to him. And he thought light was important in that regards, and he was right. But Albert Einstein, instead of getting a professorship, he eventually, through a friend of his, was able to get a job at a patent office, and he became a patent clerk. Now, that would have been a really boring job, being a patent clerk, but for Albert Einstein, it was excellent because it gave Albert Einstein time to really independently pursue his thoughts on light, especially the contradictions that we're seeing with classical physics in these experiments. So Albert Einstein will eventually realize Max Planck's quantum theory is the key to understanding this whole thing. All right. Now, Max Planck didn't understand that, but Albert Einstein eventually did. And so Albert Einstein is going to solve the issue with the photoelectric effect. All right, and we're gonna look at how he did what he did and what he thought. Okay. So Albert Einstein is going to look extensively at Max Planck's quantum theory and the idea that light is not emitted as a continuous wave with an infinite amount of energy. Instead, he's going to look at Max Planck's quantum or packets of energy. And remember that Max Planck is going to say that atoms are going to emit energy in fixed quantized energy packets, okay? Remember the staircase analogy, okay? And that once a packet of energy has been released, it's a fixed quantity and it cannot be changed, okay? So Einstein is going to look at these packets of energy, these discrete packets, and he's going to not quickly, I shouldn't say quickly, but he is eventually going to make the connection. He's going to go, aha, I get it. I understand what is going on with the photoelectric effect and the relationship to these quantized packets of energy. What Einstein is going to say is that what we're viewing here from light is really not waves whatsoever, okay? What Einstein is going to make a bold prediction is that really these packets of energy that's being emitted by atoms are really not waves, but are particles, okay? They're particles. And as you look at this flashlight here, Instead of these continuous waves coming out of them, they're packets or bundles of quantized energy. But Einstein says, they're not just packets, they're particles. Each one of these quanta, these bundles or packets of energy that Max Planck defined, they are really particles of light, each one of these. And the atoms, what they're really doing is emitting particles, not waves. Okay? Particles, not waves. And those particles are quantized, meaning that when those atoms emit those particles of light, they have a fixed quantity of energy associated with them based on the frequency. All right, now you're going to say, well, wait a minute, it's a particle, it's not a wave. And you're right, it is a particle. Okay, but we're not done. Now, Einstein is going to correctly observe these quantum packets as indeed actual particles of light. Today, we know them as photons. So all particles of light are known as photons. Now, Einstein, what he realized is that since these particles, known as photons, are quantized, they have fixed quantities of energy. So once they're emitted by atoms, the amount of energy that particle has will not and cannot change. And so what is happening that Einstein is viewing is that a particle of light, okay, known as a photon, these particles are incoming, kind of like missiles, all right, coming in from that flashlight, missiles, targeting those electrons, okay? And when those missiles, those photons of light, hit an electron, if that missile or that photon of light hits it with the right energy, it's going to eject the electron. So it's not waves hitting the electron, it is particles, missiles hitting the electron and causing it to be ejected, okay? But the only way that these missiles or these particles of light can actually eject an electron is if the particle of light has enough quantized energy to do so. If it has enough quantized energy, it will hit those electrons and eject them. Boom. Okay? So, what is that energy value based off of? Well, Einstein recognized that Max Planck was onto something. And he realized that Max Planck's quantum equation, the energy of a packet or of a quanta, is equal to HF, Planck's constant times the frequency. He realized that the experimental results suggested that there was a direct relationship with frequency and energy. As the frequency of light increases, so does the energy. Okay? So does the energy that that particle has. So what we're saying is that that particle, or not, so what we're saying is that light appears to have a wave nature to it, as well as a particle nature. And the particle nature and the wave nature coexist at the same time. And the frequency of the wave nature has a direct relationship to the amount of energy that the particle has. So as I increase the frequency of the wave nature of light, it also therefore results in an increase in the amount of energy that the particle has, or what Planck would say, that packet of energy. All right, these photons. All right, kind of seeing this a little bit. So what I really want you to think about then is that these, that light in this regards, in the photoelectric effect, we're really seeing particles called photons, or these missiles of light, smashing into electrons. And if these missiles have enough energy, it will eject the electron. But if it doesn't have enough energy, then no ejection occurs at all. The particle light just does not have a high enough frequency, therefore not high enough quantized energy to eject an electron. All right? So in that terms then, when we're thinking of intensity of light, what does intensity of light really mean? Does it really mean that we're creating higher amplitude waves with more energy? In a way, yes. But in the particle sense, no. In the particle sense, when we're increasing the number of flashlights or adding more light, all we're adding is more particles, not increased amplitude waves. And yet at the same time we are. All right, welcome to quantum. We don't understand why this is occurring. All we understand is that light has a wave nature to it, and that wave nature independently acts exactly like a standing wave. But it also has that particle nature to it. And both particle and wave nature exist in the same state at the same time. And that's crazy to think about, but that's the way it is, okay? Kind of think about this for a bit. All right, so we're almost done here. These are the two final conclusions for Albert Einstein's work, all right? Two important conclusions of the photoelectric effect. Now, Albert Einstein is not going to become famous right away. When he publishes his paper on the photoelectric effect, scientists had a hard time at first accepting it, okay? In fact, it really had to be Max Planck who recognized the genius of Albert Einstein's results that things got started. And he helped Albert Einstein really pursue his thoughts of the particle nature of light, and that it really had a dual nature of particle and wave at the same time or in the same state, okay? Scientists had a hard time with this. I mean, I have a hard time with this. I mean, everyone should have a hard time with this. This is just bizarre that light is a wave and a particle at the same time. Okay, we're not saying that a particle is a wave and the particle doesn't travel as a wave. No, they're two independent things, but at the same time, they exist. It's crazy to think about. Eventually, Albert Einstein's going to win over the scientific community, and he's going to eventually win a Nobel Prize. He actually does a lot of work, and he should win many Nobel Prizes, but he only wins one, and that is for the photoelectric effect, okay? So what I want you to do to summarize the final findings is right here, and let's just run through them really quick, write them down in your notes. Planck's quantum energy packets are really particles of light called photons. The quantized energy of a photon is proportional to the frequency multiplied by Planck's constant. The photon must have enough energy in order to inject an electron. As the frequency increases, the photon has more energy and results in a higher probability that an electron will be injected, okay? And then really, as we mentioned, at some frequencies, the photon just does not have enough energy to inject an electron, regardless of the intensity of the light, okay? So that's the first thing to summarize. The second thing is, by increasing the intensity of light, what are we really doing? All we're doing is really increasing the number of particles of light. That's it. So Einstein predicted or explained correctly that only one photon was needed to inject an electron. So again, one missile or one photon hits an electron, causing that electron to be ejected. So the more particles there are, the more missiles there are, the more probability that more electrons are going to be ejected. And that's why when we see an increase in the intensity of light, we see an increase in ejected electrons. It's just because we have more missiles, more photons of light that can hit various electrons. And each missile of light, each photon, if it has the right quantity of energy, is going to inject an electron. And so the more photons we have, or the more missiles we have, the more ejected electrons, okay? And so there it is, the photoelectric effect explained by Albert Einstein, brilliantly explained. As a result of the photoelectric effect, quantum physics and theory is going to become a dominating field in the 20th century, even up till today. And it's going to play a major impact in our understanding of the structure of the modern model of the atom and atomic theory. And so in the next few lessons, we're going to start heading in that direction of picking up back where we left off with Rutherford's model of the atom and start looking at it in terms of the quantum nature instead of classical nature, as all other scientists were looking at prior to quantum theory. Okay, so that is it for today. There's the photoelectric effect. Study your notes. Review this video as many times as you need to, okay, to get this down. So I'll say goodbye for now and see you next time.